This is part 2 of my slides on thermochemistry. We need to learn how to measure heats of chemical reactions. And to do so, we need to review the idea of heat capacity and specific heat capacity. The heat capacity of a sample of substance, any quantity of it, is the quantity of heat required to raise the temperature of that sample of substance 1 degree Celsius. Changing the temperature of the sample, then, requires a heat equal to Q. Q, again, is our symbol for heat, and that's equal to C times delta T. This is the coffee cup calorimeter that is frequently used, even in colleges, because the two styrofoam or polystyrene coffee cups are mostly air, and so they offer an excellent way to insulate from outside heat and isolate the system pretty much from any environment other than what you put in the cups, usually water. Now, there's also something called a bomb calorimeter. It's not really a bomb, but it's designed to enclose a sample that is oxidized, so that you can determine the heat of combustion, or enthalpy of combustion, of that substance. So let's do one problem. Suppose a piece of iron requires 6.70 joules of heat to raise its temperature by 1 degree Celsius. That is the specific heat capacity. The heat capacity, C. So what is the quantity of heat required to raise the temperature of the piece of iron from 25 to 35 degrees Celsius? Let's work that out. Q, the heat, is equal to the heat capacity times the change in temperature, or 6.7 joules per degree Celsius, times the change in temperature, 35 minus 25 degrees, or 67.0 joules. Here's another problem. A 30.0 gram sample of water at 280 Kelvin is mixed with 50.0 grams of water at 330 Kelvin. What's the final temperature of the mixture if no heat is lost to the surroundings? Now, we would assume that the heat lost by the hot water is equal to the heat gained by the cool water. The heat lost is equal to the heat capacity of the water, which is specific heat measured here, 4.18 joules per gram Kelvin, times the mass, 50 grams, times the change in temperature, which is 330 Kelvin minus the final temperature. The Q gained is the specific heat capacity of water, 4.18 joules per gram Kelvin, times the mass times its change in temperature, which of course is T minus 280 Kelvin. If we set these two equal to each other and solve for the temperature, we get 0.250 joules per gram degree Celsius. And again, that's just a simple algebraic change. The heat capacities are also compared for 1 gram amounts of substances. And we were using that just in this last problem. So specific heat capacity is the heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. And this is going to be specific to that substance. To find the heat required, you must multiply the specific heat of the substance times its mass and the temperature change. This is specific heat capacity. So the Q, the heat, is equal to specific heat, or specific heat capacity, we can use either set of language, times the mass of the substance times the change in temperature. So calculate the heat absorbed when a temperature of 15 grams of water is raised from 20 to 50 degrees. And it's given 4.184 joules per gram degree Celsius as the specific heat capacity. We put together our equation and we're solving for Q. So it's the 4.184 joules per gram degree times the 15 grams, the mass, times the change in temperature, which is 50 minus 20, a positive number. And so the heat is 1.88 times 10 to the third joules, or 1.88 kilojoules. Let's talk about delta H and Q. Chemists study thermodynamic changes in the system, and that's the chemical reaction that's being studied. But we're not able to measure anything about that chemical reaction in most times. What we measure are the changes in the surroundings, typically the water of the calorimeter. So delta H of the system, which is equal to Q of the system at constant pressure, is equal to minus Q of the surroundings. They're going in the opposite direction. If the reaction is losing heat, then the surroundings would be gaining heat. And so to make them equal, we have to change the sign on the Q of the surroundings. Let's talk about calorimetry. A calorimeter is a device that we use to measure heat absorbed or evolved during a physical or chemical change. The heat absorbed by the calorimeter and its contents, then, as we've seen in the last slide, is the negative of the heat of reaction. So Q of the calorimeter is minus Q of the reaction. So here's a problem. When 23.6 grams of calcium chloride is dissolved in water in the calorimeter, the temperature rose from 25 to 38.7 degrees Celsius. If the heat capacity of the solution in the calorimeter is 1258 joules per degree Celsius, what is the enthalpy change per mole of calcium chloride? So that's the problem. Now this is not specific heat capacity. This is the heat capacity of the whole calorimeter and solution in it. So first we calculate the heat that's absorbed by the calorimeter. That's going to be equal to the heat capacity of the calorimeter, 1258 joules per degree, times the change in temperature, 38.7 minus 25. If we do that calculation, we find that the heat absorbed by the calorimeter is 1.72 times 10 to the fourth joules, or 17.2 kilojoules. Now we calculate the heat per mole of calcium chloride, because all of this heat came from the dissolving of calcium chloride. It has a molar mass of 111.1 grams. So we take the mass of calcium chloride, and we're going to go into the mole hole, by dividing by the molar mass of 111.1 grams. So we now have 0.212 moles of calcium chloride being dissolved. We can now calculate the heat per mole of calcium chloride because we know the total heat that was put out by the calcium chloride into the calorimeter. So that delta H, the enthalpy of the dissolving, is equal to the Q of the reaction per mole over to the moles of calcium chloride. And that's minus 17.2 kilojoules. We had to change the sign because the heat's coming out of the calcium chloride dissolving. We're going to divide it by the total number of moles, which we have from up here, 0.212. And when we do that, we get minus 81.1 kilojoules per mole. Much of these things is available in tables on the internet or the Handbook of Chemistry and Physics, if you wanted to check to see just how close you are to the accepted value. Now we go on to Hess's law. This is a useful tool. Hess's law of heat summation states that for any chemical equation that can be written as the sum of two or more steps, the enthalpy change for the overall equation, the overall reaction, is the sum of the enthalpy changes for the individual steps. You can see this is simply a focus on what we can learn from the fact that enthalpy is a state function. So we can burn carbon all at once to CO2 or in steps, first burning it to carbon monoxide and then burning it further to carbon dioxide. So if we take the graphite, carbon, and burn it directly to carbon dioxide, we see a delta H of minus 787 kilojoules per mole. On the other hand, if we first burn it to carbon monoxide and oxygen, the question, of course, is the burning of carbon monoxide with oxygen to form carbon dioxide, do these two steps equal this step? Well, we know they must, or the law of conservation of energy is false. And so if you take minus 221 and you then add to it minus 566, which is going in the opposite direction, you see that it's equal to minus 787. So it doesn't matter how you get from here to the carbon dioxide. We've talked an analogy of going directly from point A to point B or going this way. Now the work is different, but the enthalpy change is the same. So you're changing the altitudes here of 3,600 feet, and it really doesn't matter if you do more work going up the easy route but long route or go on up directly. The change in altitude is the same. So suppose you're given the following data about sulfur reacting with oxygen to form sulfur dioxide and sulfur trioxide decomposing to form sulfur dioxide and oxygen. Could you use this to find out what the enthalpy change of going from sulfur and oxygen directly to sulfur trioxide? Well, sure you could. Here's sulfur reacting with oxygen to form sulfur trioxide. Not something that's easily done. But as you can see, we have the two reactions that can be worked with to find this. If we multiply the first equation by 2, notice, and reverse the second equation, they will add up to become the third. Because here the 2 sulfur reacting with 2 oxygen to form 2 sulfur dioxide, and then the 2 sulfur dioxide react with oxygen to form 2 sulfur trioxide. These two steps together will make the overall process of taking sulfur and 3 oxygens and making 2 sulfur trioxides. So what we have to do, we have to change the sign. Let me show that last equation on the previous slide. We have to change the sign on this because we're turning it in the opposite direction. And we double this. When we do that, everything that we don't want cancels out left and right, and we are left with the overall reaction that forms the sulfur trioxide from sulfur and oxygen, minus 792 kilojoules. The term standard state refers to standard thermodynamic conditions chosen for substances. That's 1 atmosphere of pressure and a specified temperature, usually room temperature of 25 degrees Celsius. The enthalpy change for a reaction in which reactants are in their standard states is called delta H0 or delta H0, and you can find these in tables. The standard enthalpy of formation of a substance, denoted delta H of formation 0, is the enthalpy change for the formation of just 1 mole of the substance in its standard state. There are tables for this as well. And note, very important, the standard enthalpy of formation for a pure element in its standard state is 0. Here is a table of standard enthalpies of formation at 25 degrees Celsius. We can use these to solve problems, and your teacher should be able to show you how to do that. This is a continuation of the standard enthalpy of formation tables. Finally, remember the law of summation of heats of formation states that the enthalpy of a reaction is equal to the total formation energy of products minus the total formation energy of reactants. This enables us to calculate that for any reaction.